a very strange robot arm from Tesla, and a bit more practical, I think, in context of the European Union project VCharge, where a system for automated valet parking and driving was developed. They had these designated charging spots where the vehicles were recharged using inductive charging plates. In our application, we have this more box-like object, which is the charging station, and we have to position our vehicle relative to a very specific point relative to this object. And this, of course, requires that we estimate the position of these stations very accurately. And to do this, with a camera, we have to have a very good angular resolution of the camera. And perhaps just for rough dimensions of this charging station are 0.7 meters in length, 0.4 meters in depth, and about my height. And well, as I said, the high angular resolution we achieve by having a very high resolution camera sensor, so 4 megapixels. And because it's rigidly mounted on the vehicle, we use a wide angle lens to capture enough of our scene. Also, we saw that to be able to estimate the rotation angles of the charging station very well, we have to see at least 2 sides of the charging station in our final position. Our algorithm works in a recursive fashion, and so in each new time step we update the station's pose and the pose uncertainty. And so the first thing is to, in each new time step, to predict the pose and uncertainty, and then update this state sequentially for each model feature. So we have a feature-based model, and to increase the performance and robustness, we only evaluate these features in local image patches around the predicted measurements. Also, we introduce a confidence-based feature weighting, which helps us to reduce the effect of some special error types. And this whole system, by design, is robust to partial and, well, you could say also a bit to full occlusions. The model, as I said, is a feature-based model which consists of point and line features. And these are 3D features, so they are annotated with their relative position to the object origin. So the object origin in this case is the red coordinate system on the bottom, and we have direct line segments and points. For measuring the features, the point features, we use a 2D barcode-like structure called APROTAGs, and we use only the corner points. The edge features are measured using multiple edge measurement units. So these are little image windows which measure the intensity gradients, and each edge is measured by multiple of those smaller units. We evaluated our system on simulated data against some other methods, and then also on synthetic data, which is generated video. And we see here an approach towards such a charging station, and using synthetic data we have ground truth data, so we can get a real estimate on how accurate our system is. Also, we had extensive field testing, so it was integrated into a real system. And here is shown a autonomous approach towards such a charging station, in this case a mock-up charging station. And we see it's a real-time system, and also it's quite robust. So this is a normal daylight scene, and you see how as we get nearer, more and more features are measured. But we also had the possibility to deploy it in nighttime with only a little bit of illumination. And for more information, come to our poster. Thank you.